and start solving this problem. Okay, so there are these two situations. I'll start with the first one in here. So I'm going to start with part A. So in any case, let me quickly draw this. No friction on here, so as a result, it can slide easily. And so F is the force. 50 Newton is the force. And the question is whether the upper blocks start sliding or not over the lower block, right? Does, let's say, do the blocks start sliding or not? I mean, that's the question that we would like to answer. And by just looking at this value, we cannot answer it. So as a result, we have to solve the problem. So the only way that we can solve the problem is to actually assume it doesn't start, well, assume it doesn't slide. And I mean, you just make this assumption that it doesn't slide and then solve the problem. And if it somehow doesn't satisfy the necessary conditions, then assume that it starts sliding and then solve the problem. All right, that's essentially what we are going to do. All right, so the first thing is, of course, we need to assume that it doesn't slide. Right, there are these conditions in here that the static friction force should satisfy. And after the solution, we should check if that condition is satisfied or not. If it is not satisfied, then we need to therefore do this and then solve the problem like that. Okay, that's essentially what we need to do. So I'm going to start with this, but at first I'm going to keep this as a variable. So as a result, I can insert in different values so that I can insert both of the values in here. So I'll just keep this as F, okay? And solve the problem symbolically, basically. So I'm going to assume no sliding, okay? Which means that both of the blocks actually move as one, but still, let me draw this down there. I still need to draw the free body diagram of these two objects as two separate free body diagrams. So for this one, there's a force pulling it in the leftward direction. There's a weight force, M1G, and there's a normal force applied on it. So I'm going to call this normal force as N1. And then there's a static friction force. So the problem with the static friction force is that I don't know if it is towards right or if it is towards left. I don't know this. But luckily, because of the convention that I'm using, the convention that this Fs is basically the component of the static friction force along this direction, and I allow this quantity to be negative, in that case, it doesn't matter. I know that the static friction force is somewhat along that direction, right? Either to the right or to the left. I don't know the sign of the component in here, but that's not a big problem because somehow we will be able to handle, I mean, our solution is going to handle this sign as well, okay? So that's one of the things. As a result of that, this is going to have a horizontal acceleration. So probably this acceleration is towards left, right? So let's just write this thing down. Next, on the lower block, this is not pulled or pushed. So there is a weight force applied on it. So that's applied by the earth. There is a normal force applied by the ground. So I'm going to call this as, yeah, I don't know how to draw this as a straight line. So yeah, I'm just going to explain this. So this is applied by the ground, right? But there's also, I mean, this N1 and Fs are basically the forces between these two blocks. So therefore, their action-reaction pairs should be applied on this block in here. So that means the upper block pushes this lower block in the downward direction with a force M1, and also upper block pushes the lower block in the rightward direction with a force Fs. Okay, just keep in mind that these two forces, right? The static friction force is the force between these two blocks. So as a result, if one is applied, then a force of equal magnitude but opposite direction should be applied to the other one. Similarly, it's the same for the normal force. Okay. What else? And this thing should also have an acceleration towards right, towards left, let's say, and I'll call the component A again. So again, this is how I impose again, the fact that I choose both of these accelerations to be the same is basically the constraint condition, constraint in here. I'm imposing the constraint by taking these two accelerations to be the same. This means that their relative acceleration is 0. That basically comes from the fact that their relative velocity is 0, right? Right, let me undo this. I'm just going to keep the free body diagrams as simple as possible. And then I'm going to choose my reference frame. So after all of this is done, I'm just going to choose the reference frame like that. Yeah, x-axis is towards left, why not? And then write down Newton's second law, right? So for this block, I'm going to write down the equations along the x direction, y direction. For this block, along the x direction, along the y direction. All right, let me quickly do this. This is F minus Fs is equal to M1 times A, and along the y direction, N1 minus M1G is equal to 0. Again, remember, this minus doesn't mean that I'm subtracting forces, I'm adding them. I'm adding the x components of the forces in here, and on the right-hand side, I'm writing the x component of the acceleration. Here too, there's a y component of acceleration in here, but I do this quickly. So for this one, Fs is equal to m2 times A, and what else? N2 minus N1 minus M2G, that's equal to 0. So these are 4 equations. There has to be 4 unknowns. Let me write down what the unknowns are. F is known. Fs is an unknown. Acceleration is an unknown. N1 and N2 are unknowns. So you can easily see that N1 and N2 are basically determined by these 2 equations in the vertical direction. So let me quickly do this. So N1 is equal to M1G. Insert this thing in here. So N2 is equal to N1 plus M2G. So therefore, N2 is the total mass times gravity. Okay, let me just comment on this. So basically, use this red color. This interface, they are pushing away each other by this normal force N1. And this N1 force is the force that's necessary to support the weight of this upper body in here. Okay. On the other hand, this interface in here, between the ground and the lower block, they also push each other, but they push each other in such a way that this force supports the total weight of both of these objects. So these are reasonable. So, I mean, this is one of the checks that you could do in these kind of situations. Okay, so these are reasonable. Let's solve these 2 equations. I just want to add them up. Okay, let me say add them up. So if I add them up, Fs cancels, and on the left-hand side, I have F, and I have M1 plus M2 times acceleration in here. And from here, we find acceleration. It's F divided by the total mass. And then by using this equation, then I can find Fs. All right, sorry, it's M2, right? M2 F divided by M1 plus M2. All right, this is the solution for all four unknowns are determined in terms of F. But at this point, I need to check if Fs in magnitude, obviously this is positive in here. Is this really less than mu s times n? So I have to check this because I have assumed the static conditions for these conditions to be physically, for these solutions to be physically relevant, I have to also check that this friction law is satisfied. Okay. People also ask these kind of questions, whether this is a strict inequality or equal inequality. Mathematicians may actually look at these special cases where they can also be equal to each other, but physically, this is kind of meaningless because we are always ignoring some effect that we just assume that they don't exist. Usually, this is some kind of an approximate inequality, actually. So, sliding may actually start below that maximum value, or static conditions may continue just slightly above that value. So it's not a strict boundary, it's just a blurry boundary, actually, right? You have to think of it like this. Okay, so that's basically what we need to do, all right? But let me first explain this this is something that you could have guessed, again, by using physical intuition. So since I'm assuming static conditions, both of these blocks are basically behaving as a single object, right? So that's a single object with mass M1 plus M2. Okay, so both of these objects can be considered as a single object. So I am pulling this single object with a force in the left direction, and there is no other horizontal force in here because there is no friction in here. As a result, the net force in the leftward direction is equal to the mass of the single object times its acceleration. So as a result, I could have found the acceleration without actually drawing any of these free body diagrams and things like that, okay? But I don't know, this is not something wrong because we still have to check this. But in any case, this is one of the checks that you can do, right? This is a solution that you can reach by intuition alone. And so as a result, you have to compare your solution with your intuition. Okay, so let's then, I was using that value, so let's check this. Okay, so F equals 50 newtons. So in that case, Fs is equal to, I think this was 40 kilograms. This is 50 newtons. So it's 40 divided by 50, so that's 40. Sorry about that. No, that's true. That's 40 newtons, therefore. Did I make something wrong? Yeah, no. What was mu s? Mu s was equal to 0.6. So mu s times n. So that's mu s times m1g. So that's 0.6. Mass was 10 kilograms. So therefore, this is 100 newtons. So that's 60 newtons. So as a result, Fs is less than mu s times n. So 40 is less than 60. So therefore, everything is satisfied. So as a result, the conclusion is yes, the blocks do not slide relative to each other. Okay. So that's part A. Part B, when F is equal to 100 newtons. Is there any question in this part A? I mean, we assume static conditions. We see that the static conditions are satisfied, so therefore that's okay. So that's the solution then. Now in part B, we are going to see that this is not satisfied. So in that case, Fs is equal to, I'm just going to write down the same equation in here. So that's going to be 80 newtons. And that is not less than μs times n, which is 60 newtons. And so therefore, static solution is not acceptable. Okay. So therefore, the kinetic solution. So as a result, I need to draw the free body diagrams again. Well, it's going to look the same, but I mean, the static friction force will be replaced with the kinetic friction force. Okay. So on this one, there's a weight force, there's a normal force, the force F that pulls it, and the kinetic friction force in here. So there's no ambiguity in the direction of the force. So that's definitely towards right, because I guess that the velocity is along that direction, which is also the same as the relative velocity. There's no ambiguity about the magnitude as well. So this is basically equal to mu k times n. Right? On the other one, let's see. Sorry, this is n1. So n1 is pushing it downward. Fk is in the leftward direction. There's a normal force n2. There's m2g. That's it. Okay, so as a result of that, this has an acceleration a1. This has an acceleration a2. A1 and A2, I'm assuming that they are positive. So I'm going to assume that A1 is bigger than A2, which implies that the upper block is moving towards left relative to the lower one, and the lower block is moving towards right relative to the upper one. All right. As a result, these directions of the kinetic friction force, they are consistent with each other. Okay, I mean, it looks like the picture is the same, but there are these subtle differences. So first, static friction force is replaced with the kinetic friction force. We say something about this direction because we have some, sorry, about some idea about the direction of the motion. Sorry, this is n1. That's also mu k times n1. What else? The accelerations are different. Okay. So as a result, we have one more equation in here, and so therefore one more unknown. Basically, one of the accelerations in here. So let me write down the equations. Again, along the extraction y direction, extraction y direction. Along the extraction, we have F minus Fk is equal to m1a1. Along the y direction, whatever. Along the extraction, we have Fk is equal to m2 times a2. Along the y direction, we have n2 minus n1 minus m2g, that's equal to 0. What about the unknowns? Yeah, let me write this thing down. There is one other equation in here that Fk is equal to mu k times n1. Okay, so as a result, there are 5 equations, and therefore there has to be 5 unknowns. Right, Fk, A1, A2, N1, N2. I mean, okay, so I mean, if you don't include this in here, so you just insert it in here, there are then 4 equations with 4 unknowns, but I would like to state it like this. So N1 and N2 are the same. Yeah, it's just the same. Let's see. I know Fk. Fk is equal to mu k was 0.4. 0.4. Mass is 10. Gravity is 10. So therefore, this is 40 newtons. Just like the static friction thing, force. I mean, it's just a coincidence, obviously. What else? So as a result, I can find A2. This is Fk divided by M2. So therefore, this is 40 newtons divided by 40. So that's 1 meters per second squared. Yeah, I didn't compute the acceleration in the first situation, but in any case, A1 is F minus Fk divided by M1. F was 100 newtons, Fk is 40. Mass is 10 kilograms, so therefore this is 6 meters per second squared. Fk is, why is that so? Because of this equation here. Right, it's basically coming from the free body diagram. So that's the only horizontal force in here. Okay. So in any case, so that's the solution in that case, right? Okay. There's some kind of a conceptual thing in here. So for the upper block, I'm pulling the block in the leftward direction, and there's a kinetic friction force acting on it because this is accelerating towards right. So it turns out that A1 is equal to 6 meters per second squared. For the lower block, there is a kinetic friction force pushing it in the leftward direction. And as a result of that, it's accelerating in the leftward direction with an acceleration of 1 meters per second squared. So as a result, it is moving towards left. How is it possible that the kinetic friction is in the same direction as the velocity? These are conceptual questions. Yeah, it will follow, all right. I did not understand how F static is equal. Yeah, it was just a coincidence, all right? The kinetic friction force is always 40 newtons, but the static friction force in the previous case was equal to 40 newtons for that special force. I mean, if you remember, I'm just going to go back. Where am I? Sorry. All right, sorry about that. I'm just going to go back to this, right? I assume that the force was pulling it with 50 Newton force. So it was smaller, let's say 40 Newton force or 30 Newton. In that case, the static friction force would also be smaller too. So, I mean, the static friction force will adjust its value to just the right value so that with that applied force, it will satisfy this no sliding condition, okay? So when F applied is 50 newtons, it turned out that Fs was equal to 40 newtons. It's just a coincidence. I mean, if, for example, if this F was, let's say, 30 newtons, then probably this will be like, I don't know, let's say this will be like 25 newtons, for example, okay? It will be smaller. So its value is going to change depending on the conditions. But for this case, well, Fk will always be equal to 40 newtons independent of independent of what that force is, because the kinetic friction force only depends on the magnitude of the normal force. And so that doesn't change when I apply a bigger force in there. Okay, so since the topic came up, I'm just going to look at this other question. This problem is more or less the same as that one, but this is slightly different. So, all right, I'm going to assume that there's no friction in here. Well, it doesn't matter. But there's friction in here, μs and μk. But you're applying a force on this. It's the same problem, except that the places have changed. But the solution is going to be the same. So there's no difference of that problem from the previous problem. But this is something seen in some magic shows. It's called the pulling the cloth under the table. And I think that's an incorrect thing. But the trick is something like this. So there's a table, all right? So that's a table, right? That's a table. All right, you know what a table is. So there's a tablecloth, right? Tablecloth. And there's something else in here, perhaps a vase in here. I don't know. There are these dishes and things like that on the table. The major trick is that you just pull this cloth so quickly that the things on the table stay there, so they don't come with the cloth. Have you seen this thing? Or is there anybody? Yeah, I mean, I can actually send you some videos, actually, YouTube videos. There's even a video done by these two guys, Mythbusters. They have actually done this most extreme version of it. So the table is very long, it's about like 10 meters, and then they are pulling it with some cars and things like that, right? But in any case, the trick in here is this. I mean, if this F is small, let's say F is sufficiently small, in that case, there will be some static conditions satisfied. So as a result, everything on the cloth is going to move together with the cloth because they won't be sliding, right? In any case, so you don't want this, right? So let me then undo this. If F is large, in that case, the kinetic conditions will start applying. In that case, there will be a kinetic friction force applied on these things on top of the cloth, right? There will be kinetic friction force. So there will also be a kinetic friction force applied on the cloth. So as a result, there's going to be some kind of a resistance in there. But what's important in here is that this Fk just depends on the normal force in here. So Fk is always μk times n1 in here. So that's μk times m1g. It doesn't depend on the force in here. And so as a result, whatever the force that you pull, all of these objects will have the same acceleration. Okay. So that means if you apply a much larger force, in which case this is going to have a huge acceleration, the dishes on the table are still going to have the same acceleration. So let's just say it like this. So in that case, yeah, let me say it like this. This A1 is the same in all striations, right? A1 is the same, right? So the trick is you just have to pull the cloth as quickly as possible so that, I mean, there is not much time for these to accelerate a lot, right? And so as a result, these things are going to displace on the table, but the displacement will be small because delta T is small, right? So let's say it like this. Just make sure that make delta t small. And so as a result, the displacement will be like 1/2 of a1 times delta t squared. So that's going to remain finite. So as a result, everything will stay on the table. Okay. I mean, it's just one fun way of actually applying these ideas to these kind of interesting physical situations. It's because of the, yeah, you would like to make this delta t small, and you can do this by making this force to be as large as possible, right? You just need to pull this quickly. That's the trick in there. If you pull it slowly, then everything falls down. If you do it quickly, then yeah, everything will be okay. So you may also want to make sure that this mu k is sufficiently small as well. So probably that also depends on the type of cloth that you use. I don't know. If you want to try this thing, so first try this with some non-breakable items. I don't know, something that can fall off easily and something you won't be sad about. But in any case, I mean, you can easily see that you can easily do these kind of tricks, actually, no problem with that. Okay, so, I mean, yeah, whatever. Since I mentioned this, I wanted to talk about that. So let's talk about this other question. So let me, this is a relative motion question. Yeah, I don't know. I think this is from a textbook, right? An airplane, sorry. First, there's an airplane. Yeah, whatever. Airspeed is 580 kilometers per hour. It has to fly in a straight path 38 degrees north of east. So let's see, east is that direction, north is that. North of east is like east, but it is the north of east, so that's 38 degrees. Okay, 38.0 degrees, right? So you want to fly along that direction. So basically, let me just say that I'm translating this information to the mathematics language. So it says that the velocity of the plane relative to the ground has a direction along this, right? Because, I mean, you want to move from one location to the other one, but on the map, they actually look at these 2 points, let's say. And so as a result, these positions are relative to the ground. All right. So the direction therefore relative to the ground is known. Okay. All right. What else? But there is a steady wind blowing from north. So there's a wind blowing like that. So that's the wind. So that's the velocity of the air. So I think I'm going to call this as W. So that's 72 kilometers per hour. So I know velocity of the wind, velocity of the air, right? So that's exactly known. So let's say this is known. All right. What else? The direction of this thing is known. So what about this? That's basically the velocity of the plane relative to the air. So that means, what do I know? The velocity of the plane relative to air. I don't know its direction, but I know its magnitude. So that's 580 kilometers per hour. In what direction should the plane head, right? So what we have is this, right? This is our equation. Velocity of the plane relative to air, right? That's equal to the velocity of the plane. This is relative to the ground. So I'm just going to show them by single letters. So these are relative to ground. So I know the direction of this. I know this vector. I know the magnitude of this. Okay, so somehow I would like to draw this diagram in a vector diagram so that I can decide on what the directions might be. So you may not want to work with these magnitudes. I'm sorry. You may want to, instead of working with this, you may want to work this one too. So VPA plus VA is equal to VP, right? You may want to draw the vector diagram of this one or the vector diagram of this one. Sometimes one of them is easier than the other one, right? Let's talk about this. So I know the direction of this one. So let's say that this is along that direction. So that's VP. I know its direction. So that's 38 degrees. I know the direction of this one. So how do I do the velocity difference? Difference of two vectors. I just draw both vectors starting from the same position. So that's VA. In that case, the difference in here is this. So this is VPA. Okay, so that's VP minus VA. Yeah, whatever. So that's our vector diagram. So I know this side length. I also know this side length. I know that angle, but I don't know what that side length is. All right. And this is asking me about the value of that angle. Okay. So if you want to use this one, yeah, I think you're going to get the same diagram. Probably it's a little bit difficult to start from this and then draw this. But yeah, at the end, of course, you're going to get the correct diagram. So I think the critical point in here is to translate the given information. So if it says airspeed, then in terms of your quantities, what does it mean? Okay. So I said that it means that the magnitude of that quantity is given. So you have to translate this statement given in English to the mathematical language, all right? So once you do that, then the rest becomes a little bit easier. I mean, once you translate the given information in the mathematics language, then it will become a little bit easier, but not too easy, perhaps. So how do you solve this problem? So you know this angle as well. So as a result, by using this, perhaps you can use the cosine theorem. So that means, how do you use the cosine theorem? You know the magnitude of this. You don't know this information. So this is, yeah, I mean, let me just show it like that. Okay, I'm not going to solve this problem. Let's say this is A, B, C, and that's theta. What was the cosine theorem? Let me do it like that, okay. A minus B is equal to C. Take the dot product squared, A squared minus 2A dot B. So that's cosine theta plus B squared is equal to C squared. All right, that's the cosine theorem then. So let's see. 2AB cosine theta is equal to A squared plus B squared minus C squared. So as a result in here, for example, if I say yeah, I don't know that distance. So as a result, I get a quadratic equation in here, but I don't know. That's not the best way, but you have to find some better way in here. So cosine of 128 degrees, that's equal to VA squared plus VP squared minus VPA squared. Yeah, well, at least it's an equation. So that's a quadratic equation in terms of VP. So once you find that side, then you can find this angle by applying the cosine theorem along the other direction. I don't know. I mean, there's a mathematical trigonometric way of solving these kind of problems. Usually in exams, I don't ask these kind of questions. I mean, I don't ask questions that involve too much mathematics in there. So I tend to ask questions where the mathematics part is a little bit easier. If it's a quadratic equation, then it is easy to see, to find the solutions. Okay. Do we have VP? No, this is the velocity. The plane flies within the air, right? So as a result, when you are specifying the speed of an airplane, you are specifying it with respect to air. So it has nothing to do with the ground. So the ground might be moving extremely fast, for example, but relative to the air, the plane has the same speed. If it is moving with the with this normal engines, right? With the normal engine functions. It has nothing to do with the speed of the ground relative to the air, right? It has nothing to do. So when it specifies that the speed of the airplane is 580, well, it is relative to the air. Okay, because I mean, when the plane is flying, it's the interaction between the plane and the air molecules which pushes it forward, and then it gives this final speed, right? So as a result, relative to the fixed air, I mean, if I just look at this motion from the reference frame where the air is not moving, then that's the speed that I'm going to observe. So whether there's a wind or not, it doesn't matter. That's going to be the same. Okay. So, I mean, this is basically what you should understand from the statement. So the statement doesn't tell you exactly, precisely that this figure is relative to air, because you never see this, right? I mean, if you just look at, for example, Turkish Airlines, if you ask somebody there, what is at which speed your airplanes fly, they won't tell you that, well, we are going to fly relative to the air with this, or relative to the ground with this. No, they don't. It's about like 1,000 kilometers per hour, but relative to air. So in some days, there are some certain winds in there, up there, which can actually change the speed relative to the ground. So there is always a change in the arrival times for these kind of flights. Okay. So first, let me stop this, then I'll answer your question.